Okay, so this is the second part of the second lecture, and we're going to continue that one. We ended the first part with the critical buckling load, pi squared EI over KL, quantity squared. We called that equation 1, where P critical is the critical buckling load, E is our modulus of elasticity of the column material, I is the moment of inertia of the section, usually in the weak axis. L is going to be the column length. And we just implemented this new idea of a K, an end condition column constant, where the length of the half wave for that column is relative to the pinned condition, or as I like to call it, more of a pinned ruler condition. Now, Mr. Euler, I should call him Professor Euler, derived this equation for what we would call a slender column. And that means we're going to have to identify different categories of columns based on their behavior, because the Euler buckling equation does not work for all kinds of columns. So in general, we're going to talk about slender columns and short columns. The slender columns are going to act more like a long skinny thing, and the short columns like a short wide thing. We're going to use a geometric property to define this particular feature of how it behaves. And we're going to call it the slenderness ratio. Okay? Slenderness ratio is what we call the effective length over radius of gyration. Effective length being KL and R being radius of gyration. This is our equation number 2. And I'll go ahead and define all of our terms, where our K is the column constant, well, perhaps I should back up and say the end condition constant. L is the column length. LE is an effective length. And R is a radius of gyration. Okay, so before we totally jump into this, we can see we have several new terms. We've got this effective length term, which is going to be related to K and L. We can already see that, and it hints at what the definition will be. And then we also have this radius of gyration, R, which maybe we don't know a whole lot about, but if we kept our slenderness ratio to be unitless, we know, or we can pretty much guess, that our radius of gyration needs to be in inches. Okay. These are our two new terms that we need to identify. And so we'll start with effective length, where we do in fact define effective length as the column constant times the length of the column. As a modification of that column to account for the behavior from the difference in end conditions. When we started with Euler's assumed column and we loaded it, we found the half wave, shown in blue here, to be one length of the column in our case for this example. Whoops. Here. And over on the right-hand side, since we had a fixed free end condition, we ended up having our sine wave to be 2 times the length. So our K is 2, so our effective length is going to be 2L because it's behaving like a member that's twice as long. Okay, so let's look at our next term that we needed to define, the radius of gyration. Okay, this is a geometric property of the section. Okay, so we need to look up the value of the moment of inertia and the value of the cross-sectional area. Okay, we will define radius of gyration with this particular relationship, where moment of inertia is area times the radius of gyration squared. Okay, that's going to be our equation 3. And if we go ahead and solve for R, we can get R is the square root of I over A. And this will be our equation 4. Okay, I'll write out the units, where R is the radius of gyration, I is the moment of inertia. Remember, that needs to be the weak axis, or the minimum possible. A is the cross-sectional area of the section. And I believe that sets up all of our definitions for us. So we can go ahead and look at comparing and setting up how do we know whether or not a column is short or slender. But before we really do, let's start with an example. We have an A36 steel column. Load is 15,000 pounds on this column. It's going to be a fixed pinned column, 25 feet length, and it is a W6 by 25. We're given the section itself. We are asked to find what is the slenderness ratio. So first of all, we know that the slenderness ratio is the effective length over R, which is KL over R. We can look up our R value from the table, or we could calculate it using I over A, quantity square root, and look up the other two. We already had the 9.32 inches to the fourth and the cross-sectional area of 4.43 inches squared. When we cancel those out, we will end up with an inches for units and a value of 1.45 inches. That's our R value. Okay, let's move on to the next page. I will draw out my column, fixed pinned end condition, fixed pinned end condition. I can go ahead and erase some of this stuff. Which to me looks a lot more like a roller than anything else, but we'll go with it. And it had length 25 feet, which was 300 centimeters, or inches, centimeters. Our p-value is 15,000 pounds. And that pretty much sets up the modeling. So let's go ahead and just calculate that slenderness ratio. Effective length over R. We calculated the R to be 1.45 inches. Our LE is going to be KL, which because of the end conditions is 0.7, 300 inches over 1.45. I get 144.8. So my slenderness ratio, if I answered the question, 144.8. And now we ask, so what? What does this mean? Why do we care? Well, we need to know which category to put our column in so that we can choose the appropriate mathematical relationship for the modeling. But what does this tell us? So let's go ahead and look at what we're going to compare this value to. We're going to compare the slenderness ratio to a value of a constant that we call the column constant. C, capital C, sub little c for short. And the equation is 2 pi squared E over sigma y quantity squared. This will be our equation number 5. This is the definition of column constant, where E is still the modulus of elasticity of the material. Sigma y is the yield stress. And C sub c is the column constant. If we need to use this definition in our example 1, we can calculate it. Column constant for this example was 36,000 psi, 2 pi squared times 29 million psi. I get a column constant of 126. And again, so what? Well, we use this column constant and the slenderness ratio to determine which formula to use. In our example 1 continued, we calculated a slenderness ratio. Got to go back and look. Of 144.8 and a column constant of 126. Okay, so we can see clearly that the slenderness ratio is bigger than the column constant. And so it turns out that if the slenderness ratio is greater than the column constant, then we're supposed to use Euler's equation. All right, because it's relatively long and slender. But if the slenderness ratio is less than the column constant, then we use what we call the Johnson formula. So these are both for buckling. This is for buckling as well. Now, this Johnson formula is kind of complicated, so we'll get to it in a moment. But first, let's finish our example 1 up here. So given these rules, if the slenderness ratio is greater than the column constant, so we have this first condition, then we're going to go ahead and use the Euler equation. And that was appropriate, since we already did that. Great. So let's put the numbers to that game a little bit. P critical using Euler, pi squared EI over KL quantity squared. We get pi squared 29 million PSI, moment of inertia was 9.32 inches to the fourth. KL was 0.7 times, pretty sure this is 300 inches, quantity squared. Let's go ahead and check our units just to make us feel good. Square inches and the inches squared, we'll get rid of this and we'll end up with just pounds, which is what we want. And so we feel pretty good about that. And I get a value of 604,000. Nope, I'm sorry, I misspoke. 60,488 pound force. That's our P critical. Okay, so if our actual load was going to be 15,000, and that's much smaller than P critical, then buckling is not a concern. And that's the answer to our question, right? Because P critical is that. I want to point out here one more thing. We can calculate our safety factor even against buckling. I should call this failure. Our failure load over our actual load. In this case, it's P critical over P. I had like approximately 60,000, and we were actually loading it around 15,000. So it's about a safety factor of 4 against buckling. That's a pretty decent safety factor, so I'm not concerned about it. In fact, I get safety factor, if I did all the numbers exactly, 4.03. Okay. Now that we've got this particular example worked out, let's go ahead and go back to the short columns because I told you that we would use a different equation. So let's do that. We're going to go over and look at the Johnson equation. The Johnson equation is going to define P critical to be the area of the section times sigma y times the quantity 1 minus KL over R quantity squared times sigma y over 4 pi squared E. Okay, this is our equation number 6. We're going to refer to this as the Johnson equation for short columns, where, and I'm going to take a couple shortcuts. Oh, okay, where P critical is the same, it's the critical buckling load, the area of the cross section of the member, sigma y is the yield stress, K is our end condition constant, L is the length of the column, E is our modulus elasticity. Okay. And I can't forget the radius of gyration. So this is our new column critical buckling load for short columns when the slenderness ratio is less than the column constant. Okay, let's go ahead and do an example problem. if we already did one with Euler, do you think this particular example problem is going to still be Euler? I would guess not. Example 2. We are given a 4-foot long column. So our L is 48 inches. It's a C12 by 25 channel. It's made of A36 steel. Channel is mounted with fixed free end conditions. Do you remember what K that is? There's your hint. And our load, 25,000 pounds. And the question is, find or answer the question, is buckling a concern? Okay, we need to come up with a strategy. Because to know if buckling is a concern, we need to calculate buckling. I'm going to go backwards here. Buckling. We need to calculate what the buckling load is and compare it with our P. Okay, but to get buckling, we need to know which equation, right? And to know which equation, we need to know the slenderness ratio and we need to calculate the column constant. Okay, so that's our strategy. Number 1, calculate the column constant, and the slenderness ratio. Number 2 will be choose the equation to use based on that inequality. And finally, calculate the buckling load and compare P critical versus P. That's our strategy. These are the steps that I'm going to follow. So we'll get started with our solution. Okay, so to do this equation, to do this project, since it was fixed free, and we were going to put a load of 25,000 pounds on that column, we've determined that this K value is going to be a 2 from previous work. We can calculate our slenderness ratio and our column constant. So let's start with the slenderness ratio. That's going to be the effective length over R, which is KL over R, which I'm going to do 2 times our 48 inches, because our length of member was 48 inches. And that will be divided by our radius of gyration of this particular channel type. You can look that value up, 78.78 inches. And I get a value of 123. Okay, we're going to compare this with the column constant, which is 2 pi squared E over, what was it, sigma y? And quantity square root. So 2 pi squared times 29 million psi divided by 36,000 psi, and that's a square root of all of that, right? So I get a column constant of 126. So my slenderness ratio of 123 is less than the column constant of 126. Therefore, it is a short column. Therefore, use the Johnson equation. Okay. So let's do that. ahead and continue our example. And we'll use our Johnson equation, P critical, A sigma y, quantity 1 minus, we've got sigma y times KL over R squared over 4 pi squared E. Okay, so we'll start plugging in. I looked up and my area is 7.35 inches squared, 36,000 psi times 1 minus 36,000 psi. I'm going to do the KL over R here in a second. 4 pi squared, 29 million. My radius of gyration was 0.78 inches. My K was 2, and my length was 48 inches. All that quantity squared. Let's do a unit analysis just to make sure. My inches and inches cancel, so this is unitless, and then my PSI cancel, making this entire thing unitless, which I feel good about. So we'll go ahead, continue this example, and we will calculate P critical using the Johnson formula. A sigma y 1 minus, it was 4 pi squared E on this side, and it was sigma y KL over R, quantity squared over here. And I think I got that right, so let's start plugging in. We have 7.35 inches squared times 36,000 psi times 1 minus, got 4 pi squared times 29,000. I'm writing it in like this so that I make sure I have enough space. This is just easier for me to do the bottom and to kind of estimate my space. 36,000 psi, and then I have to do a KL over R, quantity squared. So R was the 0.78 inches, K was 2, and my L was 48 inches. I think we got all that right. So let's do our unit analysis. And my inches cancel, giving me a unitless value here. My PSI cancels, giving me a unitless value for this entire. So I'm feeling pretty good about my units. When I get a P critical multiplied out of 138,556 pound force, I probably don't need that many sig figs, and that is my P. So I'm feeling pretty good about my unit analysis. So when I calculate it all out, I get a P critical 138,500. I get 66 pound force. That's too many sig figs. And that's that answer. But that is not the correct answer for the problem. Go back and check that every time. Make sure you answered the correct problem, because in this case, if I just leave it here, the answer is wrong, because the question was, is buckling a concern? In order to answer that question, I have to compare P critical with the intended load. Oh boy, what was the intended load? 25,000 pound force. Okay, and if I do if I do this comparison, P critical is much bigger than our load. In fact, our safety factor is about 138 over 25. So we have a safety factor of, oh, I don't know, 5.5. So because P critical is so much bigger than my value of P, but with a safety factor of more than 5, I can say that buckling is not a concern because I have a safety factor more than 5 against buckling. Okay, I hope that's pretty clear. I'm going to wrap this up by sending you off to do your homework. Remember, you're going to need to determine if the column is a slender column or short. In order to do that, you have to calculate the slenderness ratio and the column constant. We had some new terminology, radius of gyration. We had an effective length. You were able to compare these two values between each other. And then if the slenderness ratio was larger, then you could use Euler. And if the column constant was larger, then you use the Johnson equation. All right. Your biggest issues are going to be choosing the right K value, looking up in the tables, keeping your units straight, just doing the calculation properly without mistakes, and quite honestly, just getting everything copied down without mistake. So I'm going to just say copying, writing the right equation down. These are our biggest challenges because beyond this, it's really just plug and chug. So go ahead and do the homeworks that are there, do them on engineering paper, and we will move forward. So good job, everybody. Thank you for your time.